The next item on the agenda is a technical update on fuel channel fitness for service in Canadian nuclear power plants as outlined in CMD 18 M4. Again, Mr. Frappier, the floor is still yours.
Thank you, and good morning again, Mr. President, members of the Commission. For the record, my name is Jerry Frappier. I'm the Director General of the Power Reactor Regulations. With me today are Mr. Glenn McDougall, a specialist from the Operational Engineering Assessment Division, Mr. John Jin, the Director of that division, and Mr. Milan Ducic, a Regulatory Program Officer within the Pickering Regulatory Program Division. The purpose of today's presentation is to give the Commission members a technical briefing on the science behind the regulatory oversight of fuel channels fitness for service. This is being done in anticipation of licensing hearings for Pickering and Bruce that are going to be coming up later this year so that the Commission could have some technical background. This is, of course, not the first time we've talked about pressure tubes to the Commission. Since 2014, issues related to fuel channels and pressure tube degradation have been discussed before the Commission on a number of occasions. I would like to draw your attention to the list of Commission member documents that are on the screen, which contain more detailed information from both CNSC staff and NPP licensees that have been produced in the past. And with that, I'll now pass the presentation to Mr. Glenn McDougall, who will deliver the overall presentation.
Good morning. My name is Glenn McDougall, and I'm a specialist in the Operational Engineering Assessment Division of the Directorate of Assessment and Analysis. Before beginning, I'd like to clarify that the following deck is being presented for communication purposes. It does not reflect the full depth or breadth of CNSC staff's knowledge or compliance monitoring activities. The purpose of today's presentation is threefold. First, to provide a brief overview of the CANDU fuel channel, focusing on a key component, the pressure tube. Second, to offer a glimpse into the means by which CNSC staff ensure that licensee processes and activities achieve their intended goal, which is safe pressure tube operation. And third, building on the above information, to summarize the focus of CNSC staff's current evaluations, whose conclusions will be included in the Part 1 CMDs being prepared to inform Commission decisions about the latest Bruce and Pickering relicensing applications. So first, an overview of the CANDU fuel channel. This figure shows a fuel channel in cross-section. The horizontal pressure tube, identified in red, which holds the fuel, and through which pressurized heavy water coolant passes. The calandria tube, separated from the hot pressure tube by spacers. The calandria tube sits in a large tank of heavy water called the calandria vessel. The spacers keep the hot pressure tube separated from the cool calandria tube and allow for the flow of dry carbon dioxide gas. By monitoring the moisture level of this so-called annulus gas, operators can identify potential pressure tube leaks. The pressure tubes are tightly positioned within the reactor vessel by heavy stainless steel end fittings, which also allow for coolant flow to and from the pressure tube through feeder pipes. The number of pressure tubes varies from as few as 380 in Pickering B units to 480 in the Bruce and Darlington units. Please see the appendix for more details about Canada's CANDU fleet. The conditions under which pressure tubes operate also vary according to the vintage of the reactor design, with lower temperatures and pressures in early CANDU units like Pickering A and higher values in the Darlington units. First off, my apologies for the typo in this slide. I must have missed this. It's supposed to read technical concepts. Before proceeding to a description of the pressure tube degradation and how CNSC staff regulates safe operation, I'd like to review some key concepts. Any conversation about pressure tube technology will touch on a number of interrelated themes. But rather than review all of them, I will touch on three. By doing so, I hope to offer some context for today's presentation, as well as prepare the Commission members for discussions they may hear during the upcoming Bruce and Pickering Part 1 hearings. In the next few slides, I will briefly address three concepts. First, what do we mean by the phrase fitness for service? Second, I'll quickly discuss the presence of hydrogen in pressure tubes and the uptake of its sister isotope, deuterium. Finally, in any discussion about pressure tubes, people will frequently refer to two units of operating time, and I'd like to clarify the distinction. The first concept is pressure tube fitness for service. In a CANDU reactor, high-temperature pressurized coolant flows through a number of components, collectively known as the primary heat transport system. Because this system is responsible not only for collecting heat from the nuclear reaction, but also efficiently transferring heat to the secondary system via steam generators, the integrity of the primary heat transport system is vital. This is especially true of the pressure tubes, which contain hot fuel. The CANDU safety case relies on pressure tubes to remain leak-free under normal operating conditions and to maintain fuel cooling under postulated accident conditions. When CANDU engineers designed pressure tubes, they had a specific goal in mind. Over their lifetime, the tubes would exhibit an extremely low probability of failure, irrespective of whether they were subject to normal operating conditions or accident conditions. With this in mind, the engineers incorporated redundancies into the pressure tube design. First, they designed the pressure tubes not to leak. However, bearing in mind that pressure tubes might experience in-service degradation leading to a crack, the designers deliberately incorporated features to make pressure tubes resistant to unstable cracking. Once pressure tubes have been fabricated, installed, and commence operation, one might ask, can they still perform the way the designer originally intended? So when staff reviews a licensee's fitness for service assessment, our goal is to answer that question. Before leaving this slide, I'd like to clarify the phrase in-service degradation. For the rest of this deck, I will use it to describe degradation that occurs as a result of reactor operation. At this point, it's important to distinguish between the two types of pressure tube assessments that CNSC staff review. First, assessments that are done to confirm that inspected pressure tubes are fit for continued service. In accordance with their license condition handbook, a licensee is obliged to conduct periodic inspections and compare the results against CSA acceptance criteria. If the inspection finding does not meet those criteria, the licensee must submit a fitness for service assessment for the inspected pressure tube for CNSC acceptance. These assessments cover approximately 30% of the pressure tubes in service in Ontario. In addition, CNSC requires that licensees perform pressure tube risk assessments to address the 70% of tubes that have yet to be inspected. These assessments include two that I will describe in more detail in just a minute, namely leak before break assessments and fracture protection assessments. Both leak before break and fracture protection assessments start from a worst case assumption that somehow a crack has occurred in a pressure tube without operators being aware of it. The licensee then calculates the probability that the hypothetical pressure tube will rupture. All of the assessments must meet the acceptance criteria established in the compliance verification criteria of the License Condition Handbook. Based on the results of these assessments of both inspected and uninspected pressure tubes, CNSC staff assembles a composite view of the safety of 100% of the core. As a second concept, I'd like to discuss hydrogen and deuterium in pressure tubes, because we'll see that this is an important issue in the concept of fracture toughness, which we'll be discussing in a minute. While there are 3 hydrogen isotopes, only 2 of them really have an impact on pressure tubes. Hydrogen, whose chemical symbol is a capital H, is built into every tube during its manufacture. And deuterium, symbolized by capital D, is picked up by pressure tubes when they're in contact with high temperature heavy water. Corrosion reactions result in two things. First, a thin layer of oxide appears on the pressure tube surface, and second, a small amount of the deuterium from the corrosion reaction finds its way into the tube. The amount of deuterium is so small, it is reported in parts per million. For simplicity, rather than talking about a given pressure tube having so many parts per million of hydrogen and so many parts per million of deuterium, industry rolls the two into a single value and talks about the hydrogen equivalent concentration, or HEQ. So for the rest of this presentation, you'll hear me talk about HEQ. The hydrogen equivalent concentration is not uniform over the length of a pressure tube. In this figure, we see a snapshot view of the hydrogen that you would find along a pressure tube as it operates in the reactor. The deuterium pickup, shown in red, is affected by the variation in coolant temperature, which is the blue curve, and the variation in fast neutron flux, which is shown in the green curve, over the length of the tube. The method of installation of the tube at its ends also has an impact on hydrogen pickup. Knowledge of this behavior is important for pressure tube assessments. In particular, hydrogen equivalent concentration is a key parameter for establishing the fracture toughness of a pressure tube. Hence, the circled areas at the end of the pressure tube indicate places that require enhanced regulatory focus because of reduced fracture toughness. And I'll be giving you much more detail on that in a couple of slides. Finally, I'd like to distinguish between two units of reactor operating time that Bruce and Pickering representatives may use during the Part 1 relicensing hearings. Hot hours, which is the cumulative time the primary heat transport system is above about 200 degrees C, and effective full power hours, which is the fraction of the hot hours when the when the reactor is at full power. Each of these units has a slightly different application. To illustrate the difference between the units, the slide indicates the number of hot hours in a calendar year and the corresponding effective full power hours for a typical Canadian reactor. Under the influence of high coolant temperatures, high pressure, and bombardment by energetic neutrons, pressure tubes experience a number of types of degradation. These include changes in dimension, for example, elongation of the pressure tubes, contact or interference with other reactor components, for example, the liquid safety system injection nozzles or LIS nozzles, flaws in pressure tubes, and changes in the material properties of the tube, such as fracture toughness. It is important to recognize that when they designed the CANDU pressure tube, engineers took most of these degradation mechanisms into account. Specifically, they deliberately compensated for the potential impact of certain kinds of degradation by over-designing the tube. I'd now like to switch gears from a purely technical discussion of how pressure tubes work and how they age to a summary of CNSC staff's oversight of licensee performance under the Fitness for Service Safety and Control area. This slide offers a high-level summary of key elements of CNSC's regulatory oversight of pressure tube degradation. To comply with CNSC requirements, licensees are obliged to understand each pressure tube degradation mechanism, to make appropriate plans to assess the risk posed in their particular units by each mechanism, to perform inspections and material surveillance to confirm the extent and severity of the mechanism in their particular units, and finally, to use the collected data to demonstrate that affected pressure tubes will continue to meet acceptance criteria into the future. And that's an important point. When staff looks at fuel channel fitness for service, pressure tube fitness for service assessments, we're not interested primarily in what's happening today. We're always forward-looking. To illustrate how CNSC staff's oversight process works, I'd like to take a closer look at two examples. First, a form of degradation where CNSC requirements oblige the licensee to prepare a fitness for service assessment based on in-service inspection data. So for this example, we'll look at pressure tube flaws. Second, a mechanism that by its nature cannot be measured in service, and that's fracture toughness. As we'll see in a few minutes, licensees use predicted fracture toughness values as a basis for core-wide assessments of the risk of operating uninspected pressure tubes. Let's start with example 1. The vast majority of pressure tube flaws are fairly innocuous. Once created, they exist as mere blemishes on the pressure tube surface, having neither economic nor safety implications. However, a very small fraction of flaws could potentially have serious consequences. First, the flaw is created during normal reactor operation. If local stresses and the hydrogen level are appropriate, this flaw can become a small crack. And one mechanism capable of doing this is referred to as delayed hydride cracking, and that's symbolized as DHC. Under certain circumstances, this crack can grow through the pressure tube wall, allowing pressurized coolant to leak into the leak detection system. Finally, under specific conditions, it's conceivable that that same through-wall crack could extend along the length of the pressure tube. And at this point, the CNSC defines two possible outcomes. We can either have leak before break, which is the target that all licensees are expected to meet, or we can have a condition referred to as break before leak. Before we leave this slide, it's important to recognize two things about the Canadian fleet. First, no Canadian pressure tube has exhibited active cracking since 1986. And second, while some Canadian pressure tubes have demonstrated leak before break, only one tube has ever exhibited break before leak. That was in 1983, and it involved a pressure tube material that is no longer in service in Canada. This slide illustrates the progression of steps between initiation of a pressure tube flaw and a potential small break loss of coolant accident. Through careful consideration of this progression, CNSC staff has devised a series of regulatory barriers. Should a licensee wish to begin and continue to operate a pressure tube, each of these barriers must be successfully traversed. Each of the barriers has established acceptance criteria defined by the compliance verification criteria in the LCH. Considering these figures in turn, on the left-hand side of the figure we see a new pressure tube that is yet to begin service. To qualify for installation, the tube must be designed in accordance with the CSA standard. The tube must be installed per utility procedures and then be subject to an inaugural inspection in accordance with another CSA standard. If CNSC staff is satisfied with the results of this inspection, barrier 1 has been crossed, so the pressure tube can begin service. Moving to the right, we see the inside surface of the same pressure tube where a flaw has developed. In accordance with CSA standard N285.4, the licensee must periodically inspect a sample of their pressure tubes to look for flaws just like this. If the flaw meets CSA acceptance criteria, the pressure tube is considered unconditionally fit for service. On the other hand, if the flaw does not pass those criteria, the licensee must submit a fitness for service evaluation, basically a detailed assessment of the risk that the flaw could initiate delayed hydride cracking at some point. The assessment not only covers the present time, but a defined period into the future. If CNSC staff accepts that assessment, barrier 2 has been crossed. The licensee can operate the affected tube out to a specified deadline, at which point they must re-inspect the flaw to ensure that DHC has not initiated. Moving again to the right, we see a different pressure tube. As noted on slide 20, this tube represents the second group that CNSC staff is responsible for assessing, tubes which have yet to be inspected. Since no inspection results exist for these tubes, CSA Standard N285.8 obliges the licensee to perform a different kind of assessment. A leak before break, or LBB assessment, is one of the two pillars of the safety case for CANDU pressure tubes, and I'll describe the second in a few minutes' time. An LBB assessment asks a simple question. Assuming a pressure tube has a crack and it has just begun to leak, would operators be able to identify the leaking pressure tube and safely shut down the reactor before that crack could grow to an unstable length? If the LBB assessment predicts that operators would be successful, CNSC staff agrees that LBB has been demonstrated and barrier 3 has been crossed. If, however, the assessment predicts that the crack would reach an unstable length before operators could shut down the reactor, staff refers to this situation as break before leak. And once again, I'd like to emphasize that while some Canadian pressure tubes have demonstrated leak before break, only one tube has ever demonstrated break before leak. In preparation for the next slide, I'd like to remind the Commission of the earlier slide I had depicting the elements of an acceptable pressure tube aging management program. Licensee must understand, plan, perform, and finally demonstrate that the pressure tubes meet acceptance criteria. With respect to pressure tube flaws, this table summarizes the CSA standards and CNSC regulatory documents defining requirements for each of the aging management elements. It also provides examples of the activities licensees undertake to address CNSC requirements. Notable examples include the preparation and submission of periodic inspection program plans, which detail the scope and schedule of pressure tube inspections, and the preparation and submission of fitness for service assessments done in accordance with the CSA standard and providing detailed analysis supporting a claim that the pressure tube can be safely operated into the future. We have now seen how CNSC staff assesses one type of degradation identified during periodic inspections of pressure tubes. I'd now like to contrast that with a second kind of assessment, aimed at quantifying the risk of continued operation of pressure tubes for which no inspection data is available. One example of this is fracture toughness, a key property of pressure tubes. At this point, it's important to re-emphasize an earlier comment. While pressure tubes are designed to be leak-free for life, CANDU designers allowed for the remote possibility of a crack. They deliberately built in features that would resist the growth of a through-wall crack, irrespective of how it got there. Fracture toughness is a measure of that resistance. Practically speaking, if a crack develops in a high-toughness tube, it will take a while to grow to an unsafe length. And that is the time during which operators can identify the leaking tube and take action to safely cool and shut down the reactor. Fracture toughness is a key input to pressure tube risk assessments, like leak before break and fracture protection. However, since toughness can be measured only once a tube has been removed from the reactor, licensees need another way to get the values they need for doing risk assessments. So they rely on models, which predict tube-specific fracture toughness values based on a number of parameters. As we'll see in the next slide, temperature is one such parameter. Because pressure tube toughness differs considerably over two temperature ranges, industry has developed separate models. Fracture toughness is a property shared by most structural materials. For example, the steel used in the vessels of light water reactors, or LWR. This figure illustrates the changes in toughness that occur as the temperature of a vessel increases from shutdown through to normal operating conditions. Initially, the material exhibits brittle fracture behavior. In this lower shelf regime, should a crack exist, it would quickly propagate without any increase in pressure being required. As the temperature rises, the material toughness increases dramatically, and the fracture behavior transitions from brittle to ductile. A good analogy is a garden hose. In the middle of the winter, for example, when you're flooding a children's hockey rink, the hose would easily rupture if you accidentally opened the tap a little too quickly. However, when spring temperatures arrive, a sudden pressure increase might make the hose leak a little bit, but it would not rupture. Returning to the example of reactor pressure vessel steels, once the material reaches upper shelf temperatures, it exhibits purely ductile behavior. The fracture toughness is quite high, so even if a crack existed, the tube would resist its growth. Under these conditions, the crack will not grow unless the load is increased. This last regime is where CANDU pressure tubes need to be operated. This ensures that the crack resistance of the tubes will be at a maximum in the event of a design basis accident. One might ask, do Canada's pressure tubes still have sufficient toughness to safely perform their design function? And the answer is, for the near term, yes. However, research and development has confirmed that as hydrogen equivalent levels continue to increase, pressure tubes will exhibit a steady reduction in toughness. To manage the risks associated with this decline, licensees must consider two requirements. First, during normal operation, 100% of the pressure tubes must be on the upper shelf. Fortunately, research has shown that neither hydrogen levels nor temperature affect the pressure tube behavior once you're on that upper shelf. However, when pressure tubes are operated below 250 degrees C, for example during the heat up and cool down of the reactor, the situation is more challenging. Based on a detailed understanding of how toughness changes with both hydrogen content and temperature, operators must carefully control heat transport system pressure to ensure that at each step, pressure tubes will be sufficiently tough. I'd like to take a moment to focus on that particular scenario, the heat up and cool down of the reactor. To ensure that they can meet a key CNSC requirement, licensees establish a so-called heat up cool down envelope, which operators must observe as they pressurize and depressurize the heat transport system. To create this envelope, licensees employ a fracture protection assessment, which determines the maximum pressure that a postulated crack could sustain without becoming unstable. So again, I have to emphasize, this is looking at the worst case scenario. You have a crack in a pressure tube and you have not identified it. So to develop the heat up cool down envelope, the licensees start by assuming that there is a tube out there that has that crack. A key input to this assessment is fracture toughness. As I mentioned earlier, the temperature range over which heat up and cool down occurs, known as the transition regime, is tricky because the toughness varies both with temperature and with hydrogen equivalent level. Early in life, it was pretty straightforward to devise a heat up and cool down envelope. Pressure tubes contained only a small amount of hydrogen, so they were pretty tough. In contrast, steady increases in pressure tube hydrogen equivalent levels makes the current situation a bit more complicated. With falling fracture toughness levels, licensees have found it more difficult to define a heat up cool down envelope that will allow them to pass a fracture protection assessment. In monitoring licensee management of this challenging situation, CNSC staff focus on the size of the safety margin, and that is the amount of space there is between the upper bound of the heat up cool down envelope and the maximum allowable pressure that's determined by a fracture protection assessment. Finishing off with fracture toughness, I could repeat a similar table to what was shown in slide 24. But in the interest of time, I can simply confirm that the regulatory requirements governing pressure tube risk assessments are quite similar to those imposed on licensees when they do fitness for service assessments. And second, I can confirm that licensee performance in doing these risk assessments reflects a level of effort and focus comparable to the level that they devote to addressing fitness for service assessments. Finally, I'd like to take this opportunity to compare CNSC staff's evaluation of the 2014 licensee request to operate beyond 210,000 effective full power hours with their current requests, which the Commission will be examining in the coming months, and that is to extend pressure tube life to beyond 247,000 EFPH. This slide compares the technical basis for CNSC staff's recommendations to the Commission for extending operation beyond 210,000 effective full power hours. Compares them with the issues that staff is currently considering in preparing the Commission member documents for the upcoming Part 1 hearings for Bruce and Pickering. The figure examines 6 broad groups of pressure tube degradation, as well as a licensee initiative to upgrade the methodologies they use to do risk assessments. Taking a closer look, we see the following. For most of the mechanisms, a green bar is shown, both in the lead up to the units crossing the 210,000 EFPH hash mark, which is shown in blue, and their approach to 247,000 EFPH, a hash mark shown in red. This confirms that for each of those degradation mechanisms, staff has carefully reviewed licensee provisions to manage the associated risk and has met all applicable acceptance criteria. The lighter green bars, which extend beyond 247,000 EFPH, indicate that while staff will continue monitoring licensee performance on each and every one of those degradation types, we do not anticipate a change in the outcome. For pressure tube flaws, we see a yellow bar preceding and following the 247,000 EFPH hash mark, and that's followed by a light green bar out to end of life. This represents CNSC staff's ongoing review of licensee provisions to address 2 specific issues associated with pressure tube flaws. At the present time, our judgment is that industry will complete the necessary work to return the pressure tube flaw bar to green in the near future. Finally, the figure depicts 3 bars that have remained yellow since 2014. Degradation of one type of annulus spacer, the so-called tight-fitting spacer, changes in pressure tube fracture toughness, and licensee proposals for new risk assessment methodologies. When Bruce Power and OPG announced plans to extend station life beyond 210,000 EFPH, they formed a partnership with the former Chalk River Laboratories, known as the Fuel Channel Life Management Program. This special research and development program was intended to produce the understanding, inspection, and analysis tools they would need to support safe pressure tube operation beyond 210,000 EFPH. The focal point of that program was the 3 issues that I mentioned just a second ago. So the next slide compares the status of those 3 issues in 2014 with where things stand at the present time. Taking the issues in turn, with respect to degradation of tight-fitting spacers, industry has devoted considerable time and effort to this issue, and over the past 6 years it has borne fruit. Industry has removed and carefully examined in-service spacers, developed a suite of predictive models for their degradation behavior, and has begun preparing fitness for service procedures for publication in a Canadian Standards Association document. In short, staff rates industry's current performance as green, and we do not anticipate any downturn in industry's performance on this particular item. In terms of proposed new methodologies for core assessments, leak before break, and fracture protection assessments, industry has submitted several technical basis documents and engaged in extensive meetings to address CNSC staff concerns. Based on this, 2 assessment methodologies have been accepted for use, and CNSC staff's review of a 3rd methodology is nearing completion. Overall, CNSC staff is confident that following a continued but brief period of enhanced regulatory monitoring, we will be in a position to rate industry's performance as green. Finally, with respect to fracture toughness. While industry has completed considerable work over the last 4 years, there are outstanding issues with one of the models that they are currently using, for example, the treatment of uncertainties. As well, there are new issues, including the development of an extension to that model capable of predicting fracture toughness out to 160 ppm hydrogen equivalent, which is the new end-of-life target. For this reason, CNSC staff believes that this issue must remain yellow, and this will be reflected in the Commission member documents that you will be reviewing leading up to the relicensing hearings. At this point, I'll turn the presentation back to Mr. Frappier.
Thank you, Glenn. Jerry Frappier for the record. So to close out this presentation, I'd like to summarize a couple of key points. First, some notes on the process by which CNSC staff has and will continue monitoring licensees' practices related to pressure tube degradation. And second, what will be the focus of CNSC staff's regulatory attention with respect to pressure tubes, that is, the declining fracture toughness. To ensure licensees' fitness for service programs, to ensure licensee fitness for service programs for pressure tubes meets regulatory requirement, CNSC has a comprehensive and effective approach to oversight. We expect licensees to have an in-depth understanding of pressure tube degradation, and we require routine inspections of pressure tubes. CNSC staff has a comprehensive and effective regulatory oversight, and in particular over the proposed 10-year operating license requested by OPG and Bruce Power, staff intends to provide annual updates to the Commission via the regulatory oversight report. In terms of fracture toughness, CNSC staff can confirm that research and development on the toughness issue continues under the joint Bruce Power OPG CNL project. Since the time licensees first requested Commission approval to operate pressure tubes beyond 210,000 effective full power hours to the present, CNSC's regulatory expectations have not changed. That is, licensees must routinely demonstrate that pressure tubes remain capable of meeting all of the original design intent. And finally, should the licensee propose revised or new fracture toughness models in support of future pressure tube operations, CNSC staff will expect them to demonstrate that the predictions are conservative. That completes staff's presentation. We're available to answer any questions that the Commission members might have. Thank you for your attention.
Thank you.